Hi guys, so for this video, this is the third and last video for chapter 4. You're going to make sure you need your calculator and also a periodic table. Alright, so molecular mass and formula mass are the same thing. So before we were using molar mass for elements, that's just you look on the periodic table and the mass of the element is your molar mass. It's the same for molecules, except you have to add up the masses. So it is the sum of the masses. Okay, so for here we've got water, we've got 2 times hydrogen plus oxygen is 18.02 grams, and that's equal to 1 mole. So here we've got glucose, so we've got 6 times 12.01 plus 12 times 1.01 plus 6 times 16. And if you enter it in the calculator just like that, it'll come out correct. I get 180.18, and that is grams per mole. That's how we're able to split them. They're also using AMU, but just remember when we start calculations, which we're about to, it's grams per mole. One more, calcium nitrate. So this is where it gets difficult, y'all. If you did not learn how to name, you need to make sure you know that, because now I'm giving you names, and if you don't know them, the formula, you've got to find it. Okay, so I've got calcium nitrate. There's my formula. Calcium is 40.08. Okay, and let's take a minute to talk about this. This 2 distributes to everything inside the parentheses. So I've got 2 nitrogens, but I have 6 oxygens. And I get 164.10 grams per mole, or you can use AMU. That is a 0. Okay, please let me know if you need help. This really isn't that bad though. So with that, we can use the molecular mass to equal 1 mole, and then Avogadro's number is still equal to 1 mole. Except now we're doing them for molecules instead of elements. All right, so remember, here's these trusty milligrams. Milligrams and kilograms are going to start popping up, so make sure you can convert. That was in chapter 0. So there's 1,000 milligrams in 1 gram. Okay, now we need to find the grams of C9H8O4, and that's 1 mole. C9H8O4. So I've got 9 times 12.01 plus 8 times 1.01 plus 4 times 16. I get 180.17. And it asks how many molecules, so we've got to go one more step. 1 mole of acetylsalicylic acid is 6.022 times 10 to the 23 molecules of that acetylsalicylic acid. Okay, now that we're at molecules, remember we need to cross out units that can cancel. I do 325 divided by 1,000 divided by 180.17 times 6.022. Don't forget to use E, 23. And I get 1.09 times 10 to the 21 molecules. Of C9H8O4. Again, it's important that you start writing this, because otherwise, if you don't, chapter 7 is going to be worse than it needs to be. 1.09 times 10 to the 21 molecules of that acetylsalicylic acid. Okay, we can do ibuprofen as well. Actually, let's go ahead and do the water one because it's going the opposite way. Okay, if you want to practice ibuprofen, it's the same process we just did, but with a new mass. So for the water one, we're starting with molecules. That means molecules goes down here. And mass is always going to be in grams unless they say otherwise. So the mass of water is 18.02. It did tell us that earlier, but that's just one that's commonly used. So I know it. I get 1.06 grams of water, which does make sense, and that's because that's less than a mole of water molecules, about 10 times less at least. And so it makes sense that it's, 10 times less than 18. All right, we can also find percent composition or mass percent. Both of those are used interchangeably. So here they're calling it percent of mass, and it's just mass of element over mass of compound times 100 because all percentages are out of 100. So here it wants us to find the mass percent of chlorine. So I've got Cl4 over C2, Cl4, F2 times 100. This is what we're going to do. So I've got 4 times 35.45 divided by 2 times 12.01 plus 4 times 35.45 plus 2 times 19. Don't forget your times 100. I do suggest you go ahead and do the math first, so you get rid of all the parentheses. And then you can plug it into the calculator. I get 69.6% chlorine is of that compound, Freon 112, which is a chlorofluorocarbon. Okay, mass percent really isn't that bad. The key is you need to make sure that the element is on top is the one that it asks for, but also that you account for all of them in the compound, on top and on bottom. So this one wants oxygen. Oxygen happens to be 16, so 2 of them are 32. On the bottom, the molar mass, we're looking at 60.06 times 100. So I've got 32 divided by 60.06, and I get 53.3% oxygen. Okay, one more. The amount of sodium and sodium oxide. So here's that situation where you've got to make sure you know how to write the formula. So sodium will be 23.99, but there's 2 of them. So 47.98 divided by 63.98 times 100. And I get 75.0% of sodium. Okay, again, if you need help, I, of course, have practice. But this is important as we go into our next major topic. First, we just need to compare. If it says I have 1 mole of the whole compound, I can pull out moles of the single element. So here I've got 2 of them because there's a 2 next to chlorine. This is using mass percent in a problem. So remember, percent is out of 100. So that 39% is the same as saying 39 grams out of 100 grams. Okay, so we start with our 2.4 grams of sodium. And they want to know what the mass of sodium chloride is, so that's the bottom, because that's the whole thing. So I need grams of sodium and grams of sodium chloride on top. So the whole compound sodium chloride, sodium's just 39. I get 6.15. Really, it should just be 2 sig fig, 6.2 grams of sodium chloride. Okay, let's do one more. This one's important because it tells us the formula. So you have to be able to write Fe2O3. You're always going to start with a single grams. Iron, which means grams of iron is on bottom, grams of Fe2O3 is on top. The bigger compound is going to be 100. The smaller one is whatever the percentage is. I get 83.9 grams of Fe2O3. Okay. We're not going to do this one. We're going to keep it going. There won't be any like that on the test or quiz. Really, we're going to revisit that in Chapter 7. Empirical formulas are the next calculation. So remember, these are the simplest whole number ratio of atoms in a compound. And these are the steps. First, you're going to convert the percentages to the grams. And it's basically you just take off percent, and then you're going to write grams in the place of the percent. So here's the example, 24.5% carbon is 24.5 grams of carbon. This one is an if needed situation. So is number 4. Grams to moles, so you're going to divide by molar mass of element. Because empirical formulas are per element. For number 3, you're going to divide all by the smallest number of moles. And that's just to get a whole number. If within 0.1, you round to the whole number. If not, you're going to have to multiply. So 0.5 would be times 2 because that's a half. 0.33 or 0.67 would be times 3 because that's a third. And you just need to think about fractions for the rest of them. They don't go past 4 normally. Okay, so the way I do this is I lay out the elements it gave me. This one we do not have to do step 1 because they're already in grams. So remember, we divide by the molar mass. To get moles. I do suggest you at least write 3 numbers after the decimal. Okay. Step 3, divide by the smallest. So that's 1.749, 1.749. This is to get whole numbers. So the smaller one becomes 1. The bigger one comes whatever it is. So in this case, if we were to leave it, this would be my formula. Notice that's not a whole number. So to make 2.5 a whole number, I have to multiply everything by 2. Don't forget, if you have to do step 4, you have to multiply it all by that number. Okay, here's another one. We've got carbon, hydrogen, and oxygen. So I've got CH and O. Carbon's 165, 27.8, 220.2. You are going to get used to these more common ones, their values. Okay, divide them all by the smallest, which is this top number, 13.739. Okay, so C will be 1, H will be 2, O will be 1. Because O really comes out to 1.00, so that's 1. This is our empirical formula. Really, it's just CH2O. If you want to write the ones, that's fine. If you don't, that's fine. Okay, these are ones that have percentage. It's the same process, just get rid of the percent and write grams. So 60 grams, 4.48 grams, 35.52 grams. Okay, remember we divide everything by the smallest. This one comes out to 2.25. That is a quarter, so that means all of these are times 4. So this is C9, H8, O4, and we've seen that in a calculation earlier. That's that acetylsalicylic acid. Okay, one more. So CHO 75.69 divided by 12.01. 8.80 divided by 1.01. 15.51 divided by 16. 6.302. 8.713. 0.969. So we're going to divide them by the smallest. So I get C 6.5, H 9, O is just 1 because it's 1. So because this is not whole numbers, you have to multiply it all by 2. So I get C13, H18, O2. Yes, that's big. Sometimes they are, and it's okay. Okay, the last topic for this chapter is molecular formulas. Remember, those are bigger values from an empirical formula. To find the molecular formula, you multiply the empirical formula by some number n, which is a positive integer. To find that, you're going to do the molar mass of compound divided by the empirical formula's molar mass. So let's do an example. Given molar mass, before I do that, this will always be given, the top one. Okay, so N is 86.09. the bottom, we need to find the molar mass of the empirical formula. So I've got 24.02 plus 3.03 plus 16. I get 43.05. These should come out to be very close to a whole number. That whole number in, remember, positive integer, must then be multiplied through the compound. So this molecular formula is C4H6O2. All right, let's do another one similar. We've got N is 78.11 divided by 13.02. That comes out to 6 times CH. So my empirical is C6H6. Sorry, my molecular. Okay, this bottom one's a little different. Notice it wants you to find the empirical formula first. So I've got CHNO. I'm just going to write the moles down. These are the same steps as before, so 3.328, 13.277. Notice that was not O, it's N. 3.328, so 3.328, 3.328, so I've got CH4N. That is my empirical. Molecular is 60.10. .03, so this is about 2. So my molecular for the bottom one is C2H4N2. So sometimes they will give you the the empirical formula. Sometimes you'll have to find the empirical formula and then find the molecular formula. Combustion analysis is when you combust a larger organic molecule to make carbon dioxide and water. We are not actually going to do those calculations. If you were going much farther in chemistry, you can learn it then. And organic compounds, just remember those are ones that have carbon in them, and generally either oxygen, nitrogen, phosphorus, or sulfur. Again, carbon and hydrogen are pretty common, but the main element of organic compounds is carbon. So the reason this is because compounds with ionic carbon bonding are generally inorganic, but it's because carbon will form those 4 single bonds. 2 bonds, double bonds, 1 triple, and a single. So it's very important that carbon is always going to be happiest when it has 4 bonds attached to it. So in all of these images here, they have 4 bonds attached to carbon. They may be in the form of a double or a triple bond, but there are still 4 lines attached to each of those carbons. There's some common hydrocarbons. You'll go over those more in chapter 11 in Chem 2. That's it. I hope you'll have a great day.